Hello students, this is a video on my lesson 2 in Unit 10 on exponential functions. I'm going to work through some of the problems in the problem set because I was contacted by students and they said they had a hard time. So let's take a look at the first one. A piece of yarn that measures 1 unit is cut in half. So you can see that if there's no cuts, if it's the original piece of yarn, the length of each new piece is 1 because the piece of yarn measures 1 unit. That's the information that they gave to us originally. So that's that piece of information. It asks us to complete the table at right, so we're going to have to fill in the numbers here, and I would like you to fill in 2, 3, 4, 5, etc. using positive integers, and just try to figure out the length of each new piece. I'll pause the video, and I'll let you try that. Alright, you can see where I filled in the values. I used all the values from x equals 0 to x equals 7, and my y values, my output values, are going to be 1/4, 1/8, 1/16. We're decreasing this value by multiplying it by 1/2. And all of these have decimal equivalents. You see that I put a decimal equivalent here, 0.03125, but it's all right to leave it as a fraction form. It asks which column of your table is the input and which is the output. You'll see soon that the number of cuts is going to be the input and the length of each new piece is the output, but you should remember that in general, when you're given a table, the first column is your x column and your second column is your y column. So the answer to that can be the number of cuts is the input and the length of the yarn is output. Great. It asks if it's growth or decay, and you can see that this value is shrinking from 1 to 1/2 to 1/4. It's shrinking by quite a lot. And it says, explain how you know using the number you multiplied by in the table. Well, we know that it's decay because it's shrinking in size. But we can also determine that we're taking each new piece and multiplying that new piece by 1/2 to get the next value. 1/2 times 1/2 is 1/4. 1/4 times 1/2 is 1/8, and so on. And we know that 1/2 is called the scale factor, otherwise known as the constant ratio, is a value that is below 1. As long as the value that you're multiplying by is below 1, is smaller than 1, then we know that it is an example of decay. For letter D, it asks us to determine a mathematical model that represents the data by examining the patterns. Recall that I asked you to make mathematical models in class, so I'm going to pause the video at this time. I'd like you to try to make a mathematical model based on the information that's given to you. Remember that the model is going to consist of the starting value and also the constant ratio. Think about that for a moment. All right, here are two equivalent equations that can be used. In both cases, we have the 1 value, which is our starting value. You can see up here that the starting value is 0, 1. That's the y-intercept. So the starting value, of course, is 1. And we can see that y equals 1 times 1/2 x. This 1/2 is our constant ratio. It's the number that we're multiplying the y value by every time in order to get our new y value. Using your model to determine the length of the yarn after 10 cuts, I'll allow you to try that one, and then letter F as well. I'll let you pause the video, and I'll come back when you're done. All right, here's the answer for letter E. Using your model to determine the length of yarn after 10 cuts, we know that x is equal to 10. That's what is indicated here. We took our function that we determined in section D, and we substituted in the value 10, and we got this number in our calculator, 9.7656. And it went on a little bit, and then there was an E, a -4. That E indicates scientific notation, times 10 to the. So that was 9.7656, etc., times 10 to the -4th. This is translated out into decimal form. It's always best if you leave it in decimal form rather than putting it into scientific notation. Now for letter F, we spoke about this in class. Will the output ever reach 0? Explain why. Try to explain that now, and I will come back in a few seconds. All right, the components of a correct answer are here. It says, will the output ever reach 0? You have to say no, it will not reach 0. And there are 3 different explanations as to why. We're trying to explain why it's going on. A positive number, we're starting with a positive number, remember, multiplied by another positive number, we're multiplying by 1/2, will never become negative. It doesn't make sense. Positive times positive does not give you negative, and it doesn't give you 0 either. No matter how small the number is, it can still be cut in half. any number that I can give you can be cut in half. That's how numbers work in mathematics. And also the exponential decay functions do not cross the x-axis, so they never get into the negative side. So they never touch 0 and they never become negative. Let's take a look at the next problem. You might recall this problem because it's very similar to a problem we did in class. The piece of paper is 0.01 centimeters thick. When you fold it once, it should become 0.02 centimeters thick. So folding it consecutively gives you thicker and thicker pieces of paper. Take a look at letters A and B. I'll let you pause the video and I'll come back with the answers in a moment. Alright, for clarity's sake, I annotated this problem a little bit. I underlined where it says 0.01 centimeters, which we know there's no folds yet here. When you fold it once, it becomes 0.02 centimeters. That represents one fold. So I changed the table slightly to represent the actual situation. When there's 0 folds, it's 0.01. When there's 1 fold, it's 0.02, etc. I finished the rest of the table, and I knew that I was multiplying by 2 every time. That was my common ratio. It makes sense because you're doubling the thickness of the paper, and doubling means multiplying by 2. We filled out the 4 and 5 folds, and we filled out the rest of the table. Now for letter C, determine a formula based on letter B, which was this exercise, for the thickness. Keep in mind, we're using F and T in this formula, and we're also going to be using the information of the y-intercept and the common ratio. Try that now. Alright, we've identified the thickness as the term T. We've identified the number of folds as the term or variable F, and we have constructed our formula. T is more like our Y value, our output value. The F is the input value, how many times we've folded, so that's more like our X value. How thick would the paper be if F is greater than 10? Well, we need to find what happens when F is equal to 10 and then say how thick it would be greater than. And we're going to use proper units. In this case, we're using centimeters. Try that now. And that should have been pretty straightforward of you to substitute in that value and get 10.24 centimeters. So now we are looking for the thickness of the paper if F is greater than 10, so that means that T must be greater than 10.24 centimeters. If we have 11 folds and 12 folds, 13 folds, etc., that would be more than 10.24. So if there are 100 centimeters in a meter, how many meters thick is the paper after 20 folds? Show the work that leads to your answer. So we'll find the number of centimeters after 20 folds, then we'll divide that number by 100 to get the number of meters. Try that now. And you can see the answer for letter E. If there's 100 centimeters in a meter, we have 20 folds here, which give us 10,485.76 centimeters. Then we divided by 100 to get 104.8576. We rounded in our final answer there will be about 104.86 meters of paper, but it didn't ask us to round, so it's really up to your teacher or really up to you to try to determine what you reduce it to. Once you get to this point, rounding is trivial anyway. Let's take a look at the Sierpinski Triangle. This is a representation where an equilateral triangle, of course equilateral means equal sides, equilateral, equal sides, has 1/4 of its area removed to create a new shape. 1/4 of its remaining area is taken away, etc. So it looks like sort of like a bunch of triangles. Very cute. If we remove 1/4 of the area, what fraction of the area remains? Well, that's a little simple math there. If we remove 1/4 of the area, the part that remains should be 3/4 or 3/4. We could also say 0.75 as a fraction, as a decimal. Multiply 64, that's the starting value, with the fraction that you found in A. What value do you get? Well, 64 times 0.75 should give you the same value as the second Sierpinski triangle. 64 times 3/4 should give you 48, and I'll verify that on the calculator. And our calculator seems to verify that same information. Keep in mind that if you're multiplying or doing any work really with a fraction, you should put it into your calculator enclosed in these parentheses. For letter C, it asks us to find the areas of the third and fourth pictures, that's this picture and then this picture, by multiplying by the fraction you found in A. Pause the video now and try to do those multiplications. And you can see these answers here. I multiplied all of those numbers by 3/4, and I got 36 and 27 respectively. A formula for the area that remains after n removals of area, that's just n different triangles. This is the 0th triangle, the first triangle, the second triangle, etc. So we're going to use exponentials to get this same formula. We know that our starting value is 64, So we can start with A is equal to 64. We know that our common ratio, the thing that I'm multiplying by every single time, was told to us back here is 3/4. So I'm going to put 3/4 into the formula's parentheses. That's for letter B, the common ratio. Next, I'm going to use an exponent. And the exponent is not x in this case, but n, because n is the number of removals of area. That's your exponential equation. Try letter E and F. Pause the video now and come back when you're done. And here are the answers for E and F. You should have gotten 3.604, etc. and so forth. I rounded the number that was on the calculator, but once you get this number, the rounding is trivial. Same thing for 0.203. I rounded to the nearest 10th, 100th, 1000th, but I didn't have to. It wasn't telling me to do that. I did that out of convenience sake. And last but not least, will the area ever reach 0? It's very similar to the answer to the previous problem. Try and write it out in your own words and come back and verify. And this is a very detailed response to that question. The area will never reach 0. The triangle area will always be multiplied by a positive number less than 1, so a positive times a positive can never reach 0, cannot become negative. Also, exponential graphs never intersect the x-axis, so they cannot reach the value of 0 either. In my opinion, this is the stronger part of the answer. You don't have to write this part, and I'm not confident that this is going to be sufficient to get your full points. So remember to make your answer in the mathematical form of the fact that positive numbers multiplied by each other cannot reach 0. That was the second to last problem in the problem set. I'll finish up problem number 4, and then I will let you continue studying. Below are two tables, a linear table and an exponential table. In order to calculate which one is linear and which one is exponential, we have to determine the slopes. Take a moment to look at the differences between the y values in table A and table B and determine which one has a constant slope and which one does not have a constant slope. In other words, one of them has numbers that are adding by a consistent amount, and one of them has not that. Pause the video now. All right, for table A and for table B, we determined that table A had a different addition every single time for each different y value, but for table B, it went down by 4 every single time. Very consistent, very constant. We call that a constant rate or a slope. Table B is the linear one because it features the constant rate of -4 divided by 1. For every increase of 1 in the x value, we went down 4 in the y value, so -4/1. That is a typo. It should be a period. Table A is not linear because the y values are not increasing or decreasing at a constant rate. They're increasing and decreasing using a constant ratio or a common ratio. So that's the main difference. It asks us to explain the difference between a linear and exponential pattern. Well, we know that for a linear pattern, we have a constant slope, and the graph of that pattern is going to be a straight line graph. However, an exponential pattern does not have a constant slope. It has a common or constant ratio number to be multiplied. And it also has not a straight line graph, but a curved graph. We're going to be talking more about curved graphs in the days and weeks to come, but this was just our introduction to and our exploration of exponential patterns. This was lesson number 2 from the exponential unit, unit 10. Happy studying.